Hello, welcome to this video. Today we will be talking about the choose function and one of its properties, the binomial coefficients. So let's quickly see what is the definition of the choose function. So it goes like this. First of all, you build what is called Pascal's triangle, which goes like this. So you have a 1 and just these imaginary zeros to both sides to infinity. And then you get the next numbers in the next row by adding 2, and then that will be the one at the bottom. So the imaginary 0 here will have 0 plus 1, so a 1 here. Imaginary 0 here, 0 plus 1, a 1 here. Then the imaginary zeros have 0 plus 1, so this is the 1, 0 plus 1, this is a 1, but now 1 plus 1, this is a 2, and it keeps going. 1, 3, 3, 1, 1, 4, 6, 4, 1, and just these zeros, again going on to both sides to infinity. Now, we're going to number all of these rows, starting at 0 for the first row of 1 and tracing by 1. So next we have 1, 2, 3, 4, on and on and on. And then you have the nth row, so until the nth row, you will have always a 1 on both sides, and then some number, and then another number, and just going like this, till at the end you have another 1. And what we will do is start on either sides. It's symmetrical, so it doesn't matter, and we will move k steps. So, example with the 4th row, we're starting here and we're moving, say, 2 steps. 1, 2, we'll land it at 6. So, 4 choose 2 is equal to 6. Since we're in the 4th row and move 2 steps, if we were in the nth row and moved k steps, the number we landed on is defined by and choose k, and looks like this. Now let's talk about a few things with this choose function that we will need later on. First of all, like I said, on both sides at the end you have a 1. And then if you start here and you don't move, so k equals 0, it's always going to be a 1. So, one property is, let me actually write that in red. So we have n choose 0 equal to 1 always. The next, if we start here and then move n steps, we'll always end up in the other side, which is always a 1. So another property is n choose n is equal to 1. And then finally, last property, for how we drew Pascal's triangle by adding these two, say, example, and get this one. So generalizing it, we have by definition of the choose function as labeling these numbers, we have n choose k plus n choose k minus 1. So in the nth row, and the number where you moved k minus 1 steps, and the next number where you moved k steps, and then their sum is going to be in the n plus first row if you moved k steps. So this sum will have to be n plus 1 choose k. Now that we have these properties, let's erase all of this and get to actually what we want to prove. So now let's actually talk about what is the binomial coefficients and later we're going to prove how it relates to the choose function. So it goes like this. You want to take out something like x plus y, say, cubed. Well, what do you get after expanding this out? Well, it's the formula is x cubed plus 3x squared y plus 3xy squared plus y cubed. That is the formula. Now, what if you, say, looked at the power to the n? Well, it's going to be x to the n plus, now it's going to be some number, we'll call it c1, times x to the n minus 1 times y, then another constant, call it c2, times x to the n minus 2 times y squared, and so on and so forth until we end up at the end of y to the n. And the binomial coefficients is, for the kth term here, ck. Ck, what is its formula? Ck. And the answer to that is with the power of n choose k. Now, let's actually prove that. Okay, so what we want to show, we'll prove this by induction, as you probably already guessed, that x plus y to some power n is equal to what I wrote out before, and what I wrote out earlier. I'm going to write this as a sum, as k going from 0 to n of ck times x to the k times y to the n minus k. Now, if you remember, earlier, it's c0 is equal to cn, which is equal to 1. If you recall from earlier, the c0, it's like the coefficients of x to the n, cn, the coefficients of y to the n, are both 1. So, like the sum, we also are saying c0 is equal to cn is equal to 1, which looks kind of similar to this, so that is it. Alright, now let's actually do this. So we will check the base case. So is x plus y to the first power equal to 1 choose 0 times x plus 1 choose 1 times y. Anything choose 0, 1. 1, anything choose itself, also 1. So this will be equal to x plus y, and that's obviously true. Anything to the first power is equal to itself. So that was the base case of n is equal to 1. Now, let's go on with actually proving this. So, we are going to suppose this is true for the number n, and then by that show that this is true for n plus 1. So, we're supposing, suppose we have x plus y to the n is equal to the sum, as k goes from 0 to n, of n choose k times x to the k times y to the n minus k. Now we will show that that just because of this is also true for n plus 1, which will finish our proof. Now let's see. X plus y to the n plus 1. Well, we want to use this, and as you probably already see, we will take out from the power 1 of these x plus y, so we have x plus y times x plus y to the n. And now, because of what we assumed, or you can say the induction hypothesis, because of our induction hypothesis, we can do x plus y times this, and then we'll split it up. So, x times the sum as k goes from 0 to n of n choose k times x to the k times y to the n minus k, and then we'll have plus y times the sum again, so times the sum as k goes from 0 to n of, of n choose k times x to the k times y to the n minus k. And now we'll put the x into the sum, y into the sum. And so x times x to the k is, you can get rid of this x, and this will turn to x to the k plus 1. And then we have plus y times y to the n minus k times all of this. This means that we can get rid of this plus y times and change this into plus 1. So n plus 1 minus k. Now, let's see. Here, this is the form that we want, except for the choose, and it ends at n instead of n plus 1. But the power of y is how we want. Here we have x to the k plus 1. Let's fix it by here replacing k with k minus 1. So here we'll have n minus the quantity k minus 1, which will turn to a power of n plus 1 minus k. X to the k plus 1 will turn to x to the k. This k will turn to k minus 1. And then this will go instead from 0 to n, from 1 to n plus 1. So let's write that down, everything that I just said. We'll have the sum as k goes from 1 to n plus 1 of n choose k minus 1 times x to the k times y to the n plus 1 minus k. And then we still have plus this, so plus the sum as k goes from 0 to n of n choose k times x to the k times y to the n plus 1 minus k. Let's see what this is equal to. What we will do to combine the sums, take out here the n plus first term and take out here the 0th term. So the n plus first term here, we'll have n choose n, always 1, times x to n plus 1, times y to the 0. So we'll have x to the n plus 1, and then plus the 0th term here, I have n choose 0, always 1, times x to the 0 times y to the n plus 1. So that will be plus y to the n plus 1. And then plus what we have left here. We took the n plus first term, so it's the sum as k goes from 1 to n plus 1 of all of that, and choose k times x to the k times y to the n plus 1 minus k, and then plus this we have here, but starting at 1, so k going from 1, still adding an n, that was a mistake, of n choose k times x to the k times y to the n plus 1 minus k. Now, we will combine these two sums, and, well, you can see x to the k times y to the n plus 1 minus k is the same in both. This is minus 1. But we have the n choose k and n choose k minus 1. We know that summing them will give us n plus 1 choose k. Meaning that we have, these are still x to the n. Okay, so this is still x to the n plus 1 plus y to the n plus 1. So plus y to the n plus 1, and then plus, like we said, the sum as k goes from 1 to n of n plus 1 choose k times, it's going to be times x to the k times y to the n plus 1 minus k. And now finally, notice that this is the n plus first term in this sum, and this is the 0th term in this sum. Again, because of these two properties, so we will have finally the sum as k goes from 0 to n plus 1 of n plus 1 choose k times x to the k times y to the n plus 1 minus k. And that's exactly what we wanted to achieve. So, before this video ends, I'll tell you we will use this property of the choose function to find a formula for it in the next video. So for now, please subscribe to my channel if you haven't. I'll post more content in the future like this. Finally, that is it.